My name is Kimon Ntotsis. I'm representing Greece, and I'm currently data scientist at the Biomedical Research Center in Uni of Leicester. And I'm here to present a joint work with Professors Artemiou and Karagrigoriou entitled Exploring Nonlinear Associations Between Features, a tool for capturing complex relationships. In this work, we introduced the kernel association coefficient, which is a coefficient capable to detect both linear and non-linear association between continuous features. KAC, it is based on the foundations of kernel mutual information, a measure introduced by Greton et al. So first, we will give some definitions. First, if Zk and Zn are two vectors from a matrix Z, then the polynomial kernel, which KIC is based on, is defined as follows. Here in this equation, A, C, and D are the tuning parameters. Now, let's define the centering matrix of size M as the M times M matrix C is given in equation number 1. In this equation, I is the identity matrix and J is the matrix of ones. Now, in the case of Jm is the vector instead of a matrix, then equation number 1 takes the form as can be seen in equation number 2. Now, based on all of that, the centering of a typical matrix as Z is written as in equation number 3. Now, if Fd is the associated 10-degree kernel of the reproducing kernel Hilbert space F, then the uncentered Gramian matrix G of the Zk variable is given in equation number 4. Now, as opposed to the centering of a regular matrix, as we have here in equation number 3, the centerix of a Gramian matrix is a symmetric positive semi-definite matrix with the form of equation number 5, where Fc is the resulting centered associated degree kernel of the producing kernel Hilbert space F. Now, let's define the pivot matrix in which the spectral decomposition later will be conducted in order to evaluate the association between the vectors. Mainly, this equation here in equation number 6 is the main focus of KIC. So for two vectors, Zk and Zn, we have the pivot matrix, as can be seen here in equation number 6. In this equation, Gc is the centered Gramian matrix, and Wz is the minimum of sum of columns of the centered Gramian of the corresponding vector Zk or Zn. Note that both Gramian matrices here have been defined with the use of the standardized second-degree polynomial kernel that we can see in equation number 8, and is the one that we mentioned earlier at the beginning when we defined the polynomial kernel. So the spectral decomposition of the pivot matrix can be written as we can see here in equation number 9. So since kernel KIC is based on kernel functions, we know that the majority of the original information is included on the first eigenvalue, which is the lambda 1. So the normalization of this value constitutes the coefficient between the two vectors, and is given in equation number 10. So basically, if the value is close to 0, we assume that there is no association, relationship, correlation. It's the same thing. Or if it's 1, or if it's closer to 1, then we suggest that the association is stronger. Here we can see some of the properties of the KIC. These properties can also be found in commonly used coefficients such as Pearson, Spearman, and Kendall's. And we will not stay much on this. So let's move on to see some simulation and some real case study. First, we will start with the simulation case study. This application is subjected to data generated from a standardized normal distribution. However, in the original paper, we tried also different distributions, resulting in approximately the same results. In this simulation, we have various association scenarios, meaning transformations, which unfortunately I realized later that I didn't include them in this presentation. However, It can be seen in the original paper. Basically, we perform some linear transformation in some variables based on the target variable. We also have different sample sizes in the simulations with different replication counts, basically in order to get more robust results. So the formulated dataset that we will see today is a univariate model process with 5 explanatory features, with X1 and X2 acting as the linear and nonlinear transformations of Y and the association scenarios that I mentioned here. Now, in order to evaluate KAC, we compare it with other coefficients such as Pearson, Spearman, Kendall, distance, and Hofting's coefficients. Here in this table, in table 1, we have the frequency at which Xj is identified as significant in the model. We classified a feature as significant when it has a value at least 0.5. I know that this table is a little hard to see and understand, so I will just make 2 short comments and we will move on. The first comment from this table is that KAC average type 1 error is around 9%. Meaning that 9% of the times X3, X4, and X5 are incorrectly identified as significant features. The second comment is about the true positive outcomes, meaning the times that X1 and X2 are correctly identified as significant features. So KIC exhibits the highest true positive outcomes with accuracy rate around 87%, while distance coefficient ranks second with accuracy around 82%. Then Pearson, Spearman's, Kendall coefficient follow with an accuracy rate of approximately 65%. Now, let's move on to this table. In this table, we have the percentage of times that the association of X1 and X2 with Y is considered significant, meaning at least 0.5, while the association of Y with X3, 4, and 5 is not. So the average accuracy of KIC and distance coefficient is the highest and approximately the same, around 60% in both cases, while Kendall, Spearman, Pearson, and Hofting ranked second, third, fourth, and fifth, respectively, with an average accuracy ranging from 32 to 44%. Now, here we have the same table, but for the rest of the analysis, we will exclude the last model, the last scenario, where, as we can see, all coefficients failed to work, basically. As you can imagine, this scenario was a little more complicated, and that's why all the measures failed to work. So, as we can see here, KIC is the only coefficient that does not result in non-existing accuracy. And when I'm saying non-existing accuracy, I mean it never produced 0% accuracy rates. While on the other hand, distance provide non-existing accuracy, as we can see here in 2 models. Finally, all the other coefficients provide non-existing accuracy in at least half of the models, as we can see in this version of the table. Additional to all of that, we can see additional to all of that, the accuracy of KIC is considered insufficient, as we can see in this version, in only 2 models. And when I'm saying insufficient, I mean it's less than 50%. So for KIC, the accuracy, as I said, considered insufficient in 2 models, while in distance, it's considered insufficient in 3 models, as we can see here. And for all the other coefficients, exhibit insufficient results in at least 6 out of the total 10 models. Now let's move on to a real case study based on data previously published by Ntotsis et al. So this data set includes several economic growth indicators, and based on them, we try to model the gross domestic product. We know that these indicators exhibit both linear and nonlinear associations. So based on all of that in tables 3 and 4, which is exactly the same, we can see the association rank of GDP with all Xj from highest to lowest. With bold, we symbolize the statistically significant features, meaning the ones with coefficient value at least 0.5. Here we will have only two short comments. As we can see here, KIC demonstrates the highest level of accuracy, which is the only one that managed to identify all five variables as statistically significant. We can also see that Kendall and distant coefficients perform relatively well, both by identifying the significance of 3 out of 5 regressors. So this is a very simple real case study. In the original paper, we have 5 different real case scenarios on top of the simulations that I presented earlier. So in conclusion, in this work, we introduced the kernel association coefficient as a novel coefficient for detecting both linear and nonlinear association between features. The results of the paper demonstrate that the KIC achieves optimal or sufficient accuracy rates across different models and is also suitable for data from different distributions. Additionally, it is unbiased towards a specific association pattern and it is unaffected by the sample size. Finally, we saw that KIC effectively highlight the significance of key features and their impact of the modeling or classification problems. However, KIC have some limitations that we try to address at this point. The first one is that KIC is sensitive to zero-valued data. So basically, if you have a data set with 0 values, KIC cannot perform. You have to transform the data somehow in order not to include zero-valued data. And the second problem is that when it comes to high-dimensional data set, it can be considered a computational consuming process due to all the kernel combination between the features that it has to perform in order to get the standardized polynomial kernel. So here is the relevant some of the bibliography that we used, and at this point, this work is under review in the machine learning. Do you have any question? I'm finished. I think I got a little faster than I expected. Sorry about that.
Yes, thank you for being in time. We have time for questions. There is a question in the chat. Are you able to read the question?
Oh, yeah. Is a question 6 considered standard or can we arbitrarily define the pivot matrix? If yes, what's considered in the paper? So let me just. So basically, this equation is the equation that we based on and is the one proposed by Greton et al. Basically, they used this equation in the paper. The paper are the first two in the reference list that I have. Basically, in the paper, they use a linear kernel in order to create a dependency measure, I will say, but generally not for a specific reason. We took that, which is the main pivot function, and we used different kernel matrices. Basically, even in KIC, you can use different kernel if you want. We just performed different simulations with linear polynomial kernel, RFB, Gaussian. I think we took 6 or 7 different kernels, but we saw that the standardized polynomial kernel usually performs better than all the others. But yes, this is the main function, and you can use whatever kernel you want. Basically, I think the reason that Greton et al. Used the linear kernel is because I don't remember exactly why they proposed a second measure in their paper, and they assume linearity, and that's why they used the linear kernel instead of a different one. I don't know if that's what you're asking me. Oh, I didn't share my screen, sorry. Yeah. Yeah, I'm sorry. I was talking about this equation. So yeah, I'm sorry about that. Basically, this equation that Greton et al. Proposed, but they're using in order to calculate the centered gram matrix, we're using a standardized polynomial kernel. They used the linear kernel. Basically, in the paper that we have under review at this point, here we have like simulation from also other kernel functions, but we end up proposing the polynomial kernel. However, even in the case of KIC, you can use whatever kernel you want. It depends on the specific aim. For regression models, we saw that a standardized polynomial managed to work better than all the others. But yes, you can take whichever kernel matrix you want. I cannot see the chat right now because of the sharing.
Okay, there is another question. I think you can turn on the microphone and.
So 2 questions. First is, how do you choose the hyperparameters for your kernel in this setting? And the second is, can you do like more formal statistical testings? You use this 0.5 cutoff for a strong or significant association, but can you, like in ordinary correlation analysis, perform statistical tests to identify significant features with certain error control?
Yeah, I know what you mean. About the first question, basically we tried different things. We saw that the linear polynomial kernels managed to work more properly, and then we saw that many cases, instead of the polynomial kernel, they have the tendency to use a standardized polynomial kernel. I do not remember in which paper we saw that. They're in the original reference list. But I cannot remember. I can search and set it in the chat here if you want. And when you use the standardized polynomial kernel, we saw that we have better results than the polynomial. So basically, we tried to use, I think, also different parameters, different scenarios here with different tuning parameters. For example, we saw that in most of the cases, when we do not include a constant term, we tend to get better results when set is 0. So we used different scenarios. There wasn't something specifically that led us to this result. We just trial and error based on various scenarios from various distributions, various sample size. But yeah, you can use whatever you want as the kernel function. In reality, we just saw that this specific standardized polynomial kernel can perform more precise. For the second question, you have absolutely right. We went a little arbitrary way in order to define what we considered a statistically significant variable, because also it depends on the field that you're working on. From the completely statistical perspective, we consider something above 0.5 or 0.6 to be statistically significant, but in other sciences like social sciences or medicine, we can use a 0.3 correlation to be statistically significant. So we wanted to be like in the middle. We didn't have a specific measure that we used. That's why we used cutoff point 0.5. But basically, in our results, we didn't have anything 0.4, 0.70, or 0.6, meaning that we didn't left out statistically significant variables. All the variables, because especially in the simulations, were below 0.4. So basically, even if we say 0.5 in this work, if we end up using 0.4, we will end up with approximately the same results. I don't know if that's what we're asking.
Yes, thanks.
So thank you. Are there other questions? So I have just a curiosity, just about the KAC, and it seems that it works very well with respect to the other coefficients. Do you have any vision of the reason and the theoretical guarantees on this?
I'm sorry, I didn't get your question.
Do you have any theoretical guarantees of the reason why the KAC works well with respect to the other coefficients?
Yeah, basically in most of our simulations, in half of the simulations, we saw that KIC works approximately the same as distance correlation. It's not that it can outperform each and every one. It just pretty much approximately the same as the distance correlation. And basically, we believe that this happened because of all the other coefficients tend to focus more on the linear aspect of a model, while the scenarios that we create here, for example, the 11 scenarios, we basically have one linear transformation and one non-linear. So we wanted to see how many times a measure is capable to locate both. If you see this example here in this table, I don't know if I can zoom in. Can you see it zoomed?
Yeah. Yes.
So basically here, the 100% that you see here in Pearson, we're using a linear transformation. That's why the percentage was 100%. Like all the times, it's not that Pearson wasn't capable to locate. It wasn't capable to locate no linear transformation. That's why it performs. KIC tends to perform better. And technically, when it comes to high dimensional data, to have the assumptions that the associations are linear, it's a little like a dream that we can have, because most of the times you will have both linear and non-linear associations. So how do you handle this type of situation? How you can address it? Because most of the times in medicine, for example, specifically they used Pearson correlation or another linear-oriented measure. However, due to the nature of the data that can be affected, for example, in influenza from the weather, the relationship is more of polynomial, I will say, or exponential. So they tend to remove this type of associations from their models and end up losing information.
Okay, thank you.